think 18, a couple hundred years old anyway, just for a manner of speaking. But the standard go path is you have a configuration vector. And that's plays the role of these low number of modes. And that's how you describe the system to yourself. And it has a conjugate, meaning you dot those two things together and you get a scalar number. And famous pairs that you all know about are pressure and volume, are a famous pair of, configuration and conjugate. You want the work, you take the pressure times the volume change, and it gives you some work. And if you want to do the same thing with a magnet, you take the magnetization and you do the applied field a little bit, and you get some work there. Now, if you're careful, you'll notice that magnets and gases have really nothing to do with each other. They're totally different systems. But somehow there's this mathematical structure that kind of is behind them, and it's just above it there in the notion of this configuration and this work conjugate for the configuration. So it applies to lots of different data generating systems, not just physical ones, is kind of the point of view, and that's kind of controversial, and that's the researchy part of this. So if you go to the library and look for a book on the thermodynamics of information theory, you won't find it. It's only here today, so you can find your high dimensional. Make those checks out to Dave Ford, care of, that's a joke. Okay. Tough crowd. Okay. If you want to make the checks out, go ahead. Don't let me stop you. Okay. Right. So that's the work part of the show, and then the heat part of it is famous. Entropy's been around in information theory for going on 60 years, so that you will find, but the rest of it is so we have a science already. It's been around for a long time of describing the dynamics of a low number of modes. Like the pressure in the tire. I don't ask the garage mechanic where all the molecular positions and velocities in my tire are. I just ask him to kick it or something, and he says it seems like it's full of air, and I'm happy, and I drive off. So that's my low dimensional description of a high dimensional thing, and I'm happy with the notion of pressure and the volume of my tire, and if I throw my refrigerator magnet against the refrigerator and it sticks, I'm happy. I don't need to know all the individual alignments on this 2 to the millionth degree of freedom system. I'm just happy if it sticks or if it falls on the floor, I got to pick it up. So we're happy with these low dimensional descriptions most of the time. So thermodynamics kind of has this folklore rap, since it is such a long history of success. It's kind of a victim of its own success. People identify it with kicking the tire or throwing the refrigerator magnet against the refrigerator, and they say, but isn't thermodynamics, something other than maybe what it really is, So this is an interesting paper, 1989. This guy Mori in Japan, smart guy, and did a lot of work in chaos himself. And he says, when I was a kid, we lived in the country, a lot of bikers would come up and down our road. And for some reason, I can't tell you why, but the most horrific thing that could happen is the bikers would park their motorcycles on your yard. And I can't remember why that was supposed to be horrific, but they might stop, maybe have a drink of water or pick an apple off a tree on the side of the road, but they parked on your yard. I don't know, that was like this horrific thing, So somehow Mori parked on their yard, in the sense that he did thermodynamics right on this attractor. So people think of thermodynamics as this, equilibrium, very slow, very, tame kind of a thing, which it is, but it's tame on this 1.2 dimensional thing. So he kind of took the thermodynamics and he put it on the attractor, and as his observables was these fluctuations. This thing takes the plane and smushes it. Some directions it kind of expands, and some directions it kind of mushes together. That's why it looks like a croissant with all these layers to it. So he went ahead and says, if I'm riding on the attractor, I'm going to measure locally my expansion, and that's going to be my observable. So as I run around, I just kind of measure a pressure fluctuation in tire. I'm measuring the rate of volume, the local expansion factors in these output off exponents as I run around on this attractor. And did thermodynamics with that as the observable, and everything went through just fine. So people will tell you thermodynamics is equilibrium, thermodynamics is this, is that. Well, if you get to say what your own observables are, then everything's going to be fine. So I like to think of it as I'm eating dinner, I'm eating a salad, I can take the fork and stab a cucumber and I can eat it, or I can poke myself in the ear with it. It's my fork and I was driving it, so if I want to use it for success, I can manage to do that. I can also manage to drive it into failure. So if you pick the modes right, you'll be able to make thermodynamics work for you. If you pick the modes wrong, then but it's not the fault of the theory. the theory has to meet the application at some point, and you have to make sure that you get that right. So I just wanted to dispel the myth. It's an old paper. It's 25 years old, but 15 years old. Used to be able to do math. 16. Never mind. An integer less than 20, greater than 10, number of years old, and people seem to think that thermodynamics is just this equilibrium thing, but it can be applied to complex things, even like a fractal dimensioned kind of an attractor. Okay, so the internet. So that ends our whirlwind tour of complexity, chaos, cybernetics, and thermodynamics. Wow, all in 32 minutes or whatever it's been. And so now we get to talk about the internet a little bit, which is how we started, I guess. Boom. So where is all this stuff? Don't know. Anybody have any guesses? Not to put anybody on the spot or anything. None? So there's been a couple companies that have built this Terminator technology out, and this is a slide I'm not going to name. I'm not trying to push the technology. I'm just trying to give you the example of something. Is that showing up there? Can you read those? Okay. And the stuff in the black is showing up. Can you read it? I'll read it to you. But I'll tell you the story first. Sales guy goes out to an ISP, internet service provider, and just kind of asks them. Remember, Foya said I would talk to a subject matter expert and ask. If I was going to start trying to get the names of the modes on my inertial manifold, I would ask. This kind of thing. Norbert Wiener says is as if the system was trying to do something to achieve some kind of a goal. When they asked the ISP guy, the guy that put the servers in and loaded the software on them and all this stuff, the guy that built and put them together and ordered and all the work that goes into something like that, they asked him what are his concerns. He came up with things 0 through 11, and the types of things that show up is UDP traffic, which is a protocol, which I'm sure all you guys know, that headed from their ISP and was DNS traffic, UDP and from their ISP that was not DNS traffic, UDP that's not from their ISP and is DNS traffic, so a lot of ifs and others. FTP's in there, mail's there, web's there, SQL database stuff is in there, ephemeral high port stuff is in there, this kind of thing. So you can kind of see those are the modes. In other words, it's not that hard. We don't have to really maybe have a big theorem to tell us that, the internet's trying to do the thing that we the email server is trying to do email. How hard is that to figure out? I really don't need an equation and an inertial manifold theorem to get me there. So that's kind of maybe, the thing. So there's sort of reminiscent of Norbert saying the behavior of such systems may be interpreted as directed to the attainment of a goal. He said that 60 years ago. That's a long time. And I guess I skipped through Uncle Foya says, sorry about this. Yeah, Foya says ask, which is exactly what they did. They asked their customer, what did they think, the subject matter expert kind of thing. So that hopefully brings it home a little bit. Here's a picture of some of the Therminator slide stuff. And this is just a very simple picture, and it's denial of service stuff. And, obvious and easy stuff to talk about, but that's the reason why I put it up here. The 0 through 11, the 12 modes are color-coded across the top, and it's a time series, and I guess the older traffic is on the far left, and the newer traffic is on the far right. And the colors are just sort of the dynamics of the modes. And as I go through time, the modes interact with each other, and the colors kind of braid up. And it's not my ISP, and it's not yours, but I bet everybody in the room can look at that picture on the top and tell us when things changed, right? Just because human beings are very good at pattern recognition, right? Anybody ever that can't see a change as you go from left to right across the top? No, see, everyone can see it. And the same story on the bottom, which is kind of the heat part of the signal. You can look across the bottom and you can see the big change. So here's the quote I like to put up there. Like I say, thermodynamics is kind of a bad rap. So this is from a guy who wrote the book, The Arrow of Time. And I'm sure he's a smart guy. And but I don't think he's thought about using equilibrium thermodynamics descriptively as we've done here. Because that's all that this is. It's just taking the data and the modes that were given to us by the subject matter expert and just using